How big is the largest star in the universe? You might imagine an enormous sphere of light, millions of times heavier than the sun, ruling the galaxy like a blazing god. But out in the cosmos, the giants that take up the most space aren't always the heaviest. The most massive stars burn through their lives at a furious pace, remaining surprisingly compact, while some lighter ones grow into swollen titans that could engulf entire planetary systems. Astronomers today debate whether Stephenson 218, a dying red hypergene thousands of light years away, might be so vast that light itself would take hours just to travel around its surface. Trying to measure something that immense stretches both human imagination and the limits of our instruments. How do you define the edge of a star whose outer layers fade into space like mist? And why does the size of the universe seem to defy every rule we think we understand? The answer begins not with the largest stars, but with the smallest flickers of light that could still be called stars at all. Earth is a humble sphere just over 12,700 kilometers wide. Next to it, Jupiter looms as a true giant, more than 11 times wider and 300 times more massive. Yet even Jupiter, with all its swirling storms and crushing gravity, is still not enough to ignite the fires of a star. To cross that boundary, you need far more mass, so much that gravity itself begins to change the rules. When an object grows to about 13 times Jupiter's mass, its core becomes hot and dense enough to briefly fuse deuterium, a heavier form of hydrogen. These strange objects are called brown dwarfs, failed stars caught between planet and sun. But the irony is that adding more mass doesn't make them bigger. Instead, their growing gravity squeezes them tighter, packing their atoms closer together. A brown dwarf twice as heavy as another might be almost the same size, just far denser, like compressing a soft foam ball into a steel sphere. Even at their upper limit, around 90 times Jupiter's mass, brown dwarfs remain roughly the same diameter, barely larger than Jupiter itself. Only when an object reaches about 100 Jupiter masses, or a tenth the mass of the sun, does a true transformation begin. The core grows hot enough for sustained hydrogen fusion, the defining process that makes a star. The pressure from fusion balances the inward crush of gravity, and a new sun is born. Before that moment, the universe is filled with faint, glowing objects that want to be stars but never quite make the leap. Mass alone isn't enough. The true change comes with ignition. At the bottom of the stellar ladder are the red dwarfs, tiny, dim, and almost eternal. A typical red dwarf has only a tenth of the sun's mass, glowing with a light so faint that it can be 100 times weaker than our own star. Barnard's star, one of our closest neighbors, is a perfect example, invisible to the naked eye, yet destined to outlive nearly every other star in the galaxy. Red dwarfs burn their fuel so slowly that their lifetimes stretch to 10 trillion years, longer than the universe has existed so far. Not one has yet reached old age. Move up the ladder, and everything changes. Our sun, with about 7 times the mass of a red dwarf, burns at nearly 6,000 degrees Celsius, shining 300 times brighter. It holds more than 99% of the entire solar system's mass, anchoring everything from Mercury to the distant Kuiper Belt. But that brilliance comes with a cost. The sun's lifespan is only about 10 billion years, a fleeting spark compared to the eternity of red dwarfs. Go higher still, and the contrast sharpens. Sirius, the brightest star in Earth's night sky, has roughly twice the sun's mass, yet it shines 25 times brighter and burns at 10,000 degrees. It will live only a billion years before fading, 10 times shorter than the sun's life. The more massive a star becomes, the more violently it burns its fuel, and the shorter its existence. At 10 times the sun's mass, stars like those in the Beta Centauri system unleash 20,000 times the sun's energy. Their surfaces boil at 25,000 degrees, hot enough to strip atoms of their electrons. But their lives are over almost as soon as they begin, just 20 million years from birth to exhaustion. The heavier the star, the faster the clock ticks, and then there are the true extremes, like our 136A1, the most massive star ever recorded. It holds more than 300 times the sun's mass, yet is only about 30 times wider. Imagine all that power packed into a sphere that could fit inside the orbit of Mercury, radiating with the energy of 9 million suns. The radiation it pours out is so intense that it tears away hundreds of billions of tons of its own material every second, more mass lost in a moment than all the water on Earth combined. These storms of light and plasma act like a cosmic straitjacket, holding the surface tight even as the interior rages. That's why the biggest stars by mass aren't the largest by size. Their own light keeps them from expanding. Astronomers believe there's a natural limit, about 150 solar masses, for stars formed in one collapse. Anything larger, like our 136A1, likely results from several massive stars merging into one. So mass alone doesn't guarantee size. To find the true giants, stars so swollen their surfaces stretch across the orbits of planets, we have to look at a different stage of life. When a star runs out of hydrogen in its core, its internal balance breaks. The core shrinks and heats up while the outer layers expand outward, growing to sizes that defy imagination. Galactic, perched in the Southern Cross, began life only a bit heavier than the Sun. Now, in its red giant phase, it has swelled to 84 times the Sun's radius, large enough to nearly touch Mercury's orbit. Our own Sun will meet the same fate. In about 5 billion years, it will expand nearly 200 times wider than today, consuming Mercury, Venus, and possibly Earth itself. Stars with greater mass push this transformation even further. The Pistol Star, a blue hypergent near the center of our galaxy, is about 25 times the Sun's mass, yet its surface stretches to 300 times the Sun's radius. A living globe of fire so vast that if placed at the heart of our solar system, it would extend beyond the orbit of Mars. Rho Cassiopeia, a name that sounds like music from another world. It's a yellow hypergent, a rarity among stars, glowing like molten gold in the dark sea of space. Its size defies reason, a sphere 500 times wider than the Sun, shining with a brilliance 500,000 times greater. From across the galaxy, it would look like a miniature sun cluster burning in solitude. But beauty like this comes with a price. Rho Cassiopeia is unstable, trembling on the edge of destruction. Its enormous outer layers drift and boil, peeling away into space in colossal waves of stellar wind. Every moment, it sheds millions of tons of material, a slow and graceful unraveling that marks its final act. These hypergents live short, furious lives, bright, brief, and doomed to end in silence or explosion. And yet, even among these swollen titans, one star stands above them all, the current ruler of cosmic size, Stephenson to 218. If Rho Cassiopeia is magnificent, Stephenson to 218 is unimaginable. A red hypergent so vast that if it replaced our Sun, its glowing surface would extend far beyond Jupiter, even brushing against Saturn's orbit. Light itself, racing at 300,000 kilometers per second, would need nearly 9 full hours just to make a trip around its circumference. And if humanity's fastest jet tried to circle it, that single journey would last 500 years. Its sheer size breaks the limits of comprehension. This is a star that would engulf everything we know: Mercury, Venus, Earth, Mars, Jupiter, all swallowed whole inside its burning body. What would remain of our solar system would be a dim, frozen frontier, lit only by the faint red glow of a star too big to believe. But here's the twist. Even this cosmic giant may not be what it seems. Measuring something like Stephenson to 218 is one of the hardest challenges in modern astronomy. Its apparent size depends entirely on how far away it truly is, and that distance is still uncertain. A tiny error in distance can make a star seem hundreds of times larger or smaller than it really is. Even worse, the outer layers of Stephenson to 218 aren't solid or sharply defined. They're made of thin, dusty gas that blends into space like fog. So where, exactly, does the star end? Some astronomers argue that what we're seeing isn't a surface at all, but a vast, drifting cloud heated from within, an illusion of size more than a physical boundary. Others suggest it might not even belong to the star cluster we think it does, which could mean every measurement we've made is wrong. For now, Stephenson to 218 holds its throne as the largest known star by radius, but it's a crown that could vanish with a single better measurement. In astronomy, even the biggest numbers come with a question mark. What we call certainty today might look different tomorrow. Once sharper instruments and new telescopes take another look, yet whatever its true size, Stephenson to 218 reminds us of something deeper. These titanic, dying stars are not just cosmic curiosities. They're the universe's great forges, factories where the heavy elements that make up planets, oceans, and even life itself are created. Iron, gold, oxygen, and carbon, all born in the fiery hearts and explosive deaths of giants like these. When a hypergent finally collapses, it gives everything back to space, scattering its ashes across light years. From that debris, new stars form, new planets gather, and perhaps, somewhere, new life begins. So the search continues for the next record breaker, the next impossible sun hiding in the dark. With every new telescope, every deeper look into the galactic dust, humanity reaches a little farther, chasing the edge of what's possible. Because in the end, the story of the universe's biggest stars isn't just about size or light. It's about transformation, the endless cycle of creation and destruction that builds everything we know, even the stars themselves.